Hi everybody, Dr. Pingle here. This is part 2 of our lecture on spatial interpolation. We're going to be talking today about producing smoothed grids. In lecture 1, we talked about building gridded data, rasterized data from point data. Today we're going to be working with raster products as well, but we're going to be treating things as if, rather than putting points within just sort of a fishnet grid, we're going to be smoothing them out a little bit using a couple of common techniques. So as an example, we're going to be working with a couple of, a data set that actually comes out of Chicago. So in lecture 1, we worked with some Baltimore data of 911 calls. This is a very similar data set coming from the city of Chicago's open data portal on crimes within the city. And on the left, we've got point records of violent crime. And you can sort of see an overall pattern. But as we talked about last time, a lot of these dots are overlaid one on top of another. And so it's difficult to sort of pick out hot spots very easily. The other problem with some of the feature to raster tools that we used, point to raster, is that essentially we get resulting graphics that are sort of blocky in appearance. And this is more than just a visualization problem. This is actually an analysis problem. And so we need to attend to that if we want to try to improve the overall accuracy of our visualization and of our subsequent analysis. So what we want to do is essentially apply a moving window kind of an approach to this. Now, one easy way of treating this would be to use something like focal statistics to smooth it out on the back end, and there's really nothing wrong with that approach. You can take you can use a feature to raster, point to raster, build the image that you see over on the right, and then literally apply a moving filter to the result with focal statistics. But we're going to be talking about an additional way of solving this problem, which is using kernel density estimation or point density tools, both of which are effective ways at smoothing this out a little bit. So as I said, this is really more than just a visualization problem. This is actually a problem in terms of how we think about our data, what it means. One basic problem here is that the histograms produce these sharp discontinuities, and this is actually true of our spatial data, but it's also true of statistical data presented as a histogram. The difference between an A and an A minus might be this 93%, but as anyone who has graded exams knows, if you get a 92.999, everybody in the world wants to round that up to 93. And there's good reason for that, right? That we don't always think that the world, that these discontinuities or these lines that we draw should really be as sharp as they are. Maybe we want to try to smooth this out a little bit. So in the world of statistics, what we would do is we would apply a technique called kernel density estimation to solve this problem. And when we talk about statistics, you can use these same kernel density estimation tools using something like Seaborn or built-in tools in pandas to do this on your statistical data. How do we apply those same ideas to our spatial data? The idea behind kernel density estimation techniques is essentially that the observation that we see at a given point is really represents sort of a probability curve passing through that point, and every realization that we find is a little bit rougher than it should be. So for instance, if we make a histogram of normally distributed random numbers, in this case with a mean of 0 and a standard deviation of who knows, 0.03 or something, we might get a histogram that looks something like we see here. Those irregularities we say aren't, in some sense we want to say those irregularities are not real, that they're just sort of, that's how the dice were rolled this time, but if we rolled the dice again, it would come out a little bit differently. And if instead of choosing 30 observations, we chose 3,000 observations or 3 million observations, we would expect this histogram to start to smooth out and start to approximate a lot more closely the line that we see. Every time we do a model, no matter how many instances we have, it's still going to be more irregular than the actual probability density function, which is sort of our expected outcome over an infinite amount of observations. And so as a result, what we want to do is we want to try to smooth out what we see. The discontinuities that we're seeing in our City of Chicago crime data aren't real. They're just sort of how the dice rolled that time. If you ran the same numbers on the following year, we would expect those numbers to be a little bit different, not just because of sort of actual changes of maybe behavior in time, but just by luck, right? So there's some randomness in every spatial phenomenon, and so we might want to take that into account. So one way of doing this is to apply these kernel density techniques, and we would call this an attempt to recover an empirical distribution. It's smoother than a histogram, but it's less smooth than fitting a model. So in other words, we don't just want to count things in bins. We want to smooth that out a little bit. Neither do we just want to guess or fit a normal distribution to it. And every time you do something like calculate the mean or the standard deviation, effectively that's what you're doing. And it's not necessarily taking into account the sort of minor or potentially important variations that are in your data. So this empirical kernel density technique essentially is this middle ground between fitting a model and just using something like a histogram. The basic idea behind this whole process is essentially we're going to apply what's called a kernel to our data. And here we're still imagining just sort of a one-dimensional data set visualized as a histogram of values. So we run a random number generator on a normally distributed random number generator. We get 100 results. We plot that out. How do we create a histogram, or how do we create a smoothed version of that? Well, what we want to do is apply this moving average, but instead of applying just sort of a naive moving average, which would be take the observations that are within 0.1 of my value and create the average, what we want to do is we want to apply something like a distance decay function. So the idea is that we want to weight observations according to their distance. Nearer observations are going to count more than distant observations. So we might count something that's within 0.001 with a weight of 1, but as we get further away of that, the weight of that observation starts to drop off. In the middle panel here below, we've got 6 different versions of different kinds of ways of dropping that off. And let's just talk about a couple of them. So the top hat kernel is essentially a kernel that weights all observations equally within some fixed distance. So any observation within a band of, and this is a parameter that you have to supply, but any observation within a band of 1 gets weighted at 1. But once you get outside of that range, we don't count it at all. So it's an all or nothing kind of a kernel. You're either in or you're out, and everything that's in is weighted the same. So this is, if you've done moving average calculations before, this is essentially what you've done. A more sophisticated way of doing this, though, is to weight things differentially based on their distance. So at some point, the weight drops off to 0. So let's take a look at the linear kernel. Here, everything is weighted, everything that's within sort of 0 distance, meaning the point itself, is weighted with 1. And the distance, the weight of that observation drops off linearly to some value. Now here it's given as h, but that could be whatever unit is appropriate to whatever it is that you're modeling. Maybe we want to drop off until we reach 500 meters or 1 kilometer or 5 meters. Whatever suits your data, there's no fixed answer here. It really kind of depends on the nature of the phenomena that you're trying to model. Now, middle ground versions of that would be something like the Gaussian and exponential kernels that you see. So a Gaussian kernel essentially is probably the most commonly used kernel for this kind of work. Essentially everything within zero distance gets a weight of 1. Nearby observations tend to get discounted only a little bit, but then at a certain point it starts to drop off quickly before kind of leveling out again. And if you compare that peak, excuse me, if you compare that peak to the exponential kernel, where immediately the weight starts dropping off as you move away from that central point. Those are different kinds of structures. So there are a lot more kinds of kernels than that. We'll be discussing a few more others as we go through. You can have kernels with holes in them, which actually comes up quite often with hotspot analysis. We want to not count anything within a short window, and then we want to start counting things again. The shapes of these kernels can actually get fairly complicated. So again, the shape of the kernel shown here is the blue box, expresses how the weight of the observation changes with distance. This is our most common example. This is the box or the uniform or the top hat kernel, lots of different names for this. Top hat because the shape of it sort of reminds you of a top hat. But I like to think of this as a simple moving average because almost all of you have probably been exposed to this method of calculation at some point. When you look at something like the temperature record and people want to look for a signature of temperature increases, what we want to do is we want to discount that sort of fast variation, right? So the daily kind of bouncing up between a high in the afternoon and a low at night. We don't want to count that. We want to weight things there, and maybe we don't even want that. Maybe we want to weight things according to a weekly moving average or a monthly moving average. This is often the way those things are calculated. This is the example of the linear or triangular kernel. Again, we have a maximum weight, usually nominally given here as 1, and then it drops off just as a straight line with distance up to whatever those are specified. And again, there's no fixed number of what that is. That's all a parameter that you as the user or you as the analyst has to supply. This again is the Gaussian kernel. So in a Gaussian kernel, the weight only drops off a little bit as you move out from the central point. Then it starts to drop off a little bit quickly before sort of dovetailing, asymptoting out, and then maybe it eventually stops at a certain distance point. So how do we actually apply this kind of work within ArcGIS? There are some toolkits within the spatial analyst set of tools under density. Point density and kernel density are the two that I'm going to be talking about, but there's a line density that's essentially the analog to this. So point density is going to create a raster instead of a 2D histogram with rigid boundaries. Essentially what you do is you specify a 2D kernel where points outside that cell can be counted for that cell. You can also specify what's called a population field, which means we want to weight things according to some value that's in the data. So if I have a point that might represent a number of observations, so again, if we think back to our species density maps, maybe at some grid point I saw not just one bear, but 3 bears, and I have a field that reflects that in my data, and I want to weight that accordingly. That would be what the population would be for. If there are multiple observations, or if each point in the record maybe represents multiple observations. Another example of this would be if you're trying to build a population surface of the United States, and we had the sizes of cities, that population field would literally be the population of the city. Taking a look at a couple of the other important parameters of this here. One is the output cell size. Again, these will be often calculated for you automatically, but I would encourage you not to use those automatic values and instead to set those to values that you think are the most appropriate. If you don't know what that number is, you can run the tool and you can run it again after reviewing the data. But most of the time in practice, it's nice to set that to a good round number that's appropriate to whatever it is that you're working with. That could be 100 meters, that could be 250 meters, that could be 100 miles, but whatever kind of reflects the fundamental underlying raster type that you want to generate. Making that value too fine doesn't really do anybody any good. You want to try to set that number to sort of the highest number that still facilitates the analysis that you want to do, generally speaking, to reduce the complexity in the model to a manageable level. But there's a lot of experience that goes into setting that output cell size appropriately. The neighborhood describes the shape of the kernel. We can have a number of different versions of this. Right now it's set to circle. That's likely to be most of what you're going to want to use. You're going to define a radius. That radius can be either expressed as pixel values, which matches to your output cell size, or I would encourage you probably to set that to map coordinates if you don't feel comfortable with that. In this case, if we apply a circle neighborhood with a 8 pixel radius, it's going to do a search for any points within my initial input point features that are within 8 pixels of that, and use those values to determine what my value should be. If that doesn't make sense, I would encourage you to pause the video here, think about that stuff for a moment before moving on, and certainly send questions my way if that doesn't make sense. But you'll get a chance to work with some of these ideas in the notebooks, and that should help you get a better understanding of what's going on here. So again, the neighborhood defines the kernel. This is probably the fundamental concept of what we're doing here. The circle is the most common, and we talked about how that works. But we've got a number of different kinds of things that we can use as well. We have an annulus or a torus or a donut-shaped neighborhood defined by an inner or outer radius. In several kinds of data analysis, what we want to do is we want to exclude observations that are too near to what we're doing. The logic there is that if we're trying to smooth the data, then very large, sort of abnormally large or abnormally small values, or outliers in other words, could potentially skew our data and make the statistics kind of go a little bit wonky. And if we exclude those, whether it's the point that we're at, whether it's at the exact point that we're at and we don't include ourselves in our observation, or if we don't include our neighbors, our immediate neighbors in that kind of analysis, all of that is sort of using a donut-shaped structuring element or neighborhood. A rectangle is a nice way to do it. A rectangle is essentially performing the same kind of calculation as a circle, with the exception that we're looking for anything within sort of a 3 by 3 or a 5 by 5 or whatever our neighborhood size is, rectangular array. Now, why would we define our neighborhood as a rectangle rather than a circle? Computational efficiency is the main answer. It's much easier for the computer to calculate all of the observations within a rectangle than it is for a circle. It's just easier to sort of reference 4 or 5 or 6 grid cells to the left, or 4 or 5 or 6 grid cells to the right. Whereas if we use a circle, we actually have to run a distance calculation on that. Again, that's obviously very easy for a computer to do once, but the way that the computer solves these problems is it actually marches through the whole array, the whole raster. Each point has this neighborhood calculation performed on it. And so you can imagine that as our rasters start to get pretty big, we're performing those calculations very often. And so even small improvements in computation time can make a big difference on the back end in terms of how long a model takes to run. A 1000 by 1000 pixel raster is 1,000,000 calculations, and many of the rasters that we're dealing with are much bigger than that. So if your calculation time is sort of jumping up by the square, you're really adding on a lot of work, if even with these minor changes. Less often used are wedges. So wedges are a way to define things with angles in addition to distances. So if the phenomena that you're modeling are particularly oriented in one direction or another, if that's important, you can do that. I have never in practice used a wedge-shaped neighborhood, but that's not to say that it's not useful. It's nice to have it in here. And then finally, you can have a cell map, which means, in other words, you can define the kernel in any way you want. Now, this is really effective and really useful. It means that you can you can apply this in any number of ways. And that's pretty exciting. That means that, that you can get really creative with how these neighborhoods are defined if you have a reason to do so. That doesn't come up as often, but it still does. It still does come up. Now, one of the things about all of these, and you'll see here in the second line, we're imagining this as sort of a circle as a hockey puck shape. What we're doing here is we're taking our moving neighborhood, our simple moving average calculation, we're applying that over a circle instead of just sort of a width, like we would ordinarily do with a histogram. And so kind of imagining a three-dimensional shape that fits these is a nice way to do it. All of these things are essentially flat kernels or flat structuring elements is another term for this. So we'll be looking at more interesting ways of defining those here in a second. So hockey puck shaped is your circle. Last time we talked about the Baltimore 911 data. So if you need to take a quick look back at that with the point data, you can. Essentially, again, what we're doing is we're taking each point. So we're overlaying a fishnet raster, and at each point we're putting this hockey puck down, and we are flagging those pixels that fall within the hockey puck distance. Now, the calculation actually is the reverse of that. What we actually do is we march down each of our pixels, and we apply the hockey puck on each of those, and then we add up all of the points that are within the hockey puck. But you can think of it either way. It produces the same. Result. The problem with the hockey puck, or the problem with point density tools, is that they do have this hard cutoff. So just like a histogram, we've got a hard line. You're either in or you're out. And the result is that when you run point density tools on a data set, you often get what's called artifacting in the data. So artifacting is when the visualization is producing results that are really more indicative of how the thing was calculated rather than some real pattern in the data. We don't imagine that there are these sort of, again, hockey puck shaped circles of 911 calls. That's just a function of how we did the calculation. That's not really in the data. We don't really think that as you get outside of one of these circles, we expect the 911 call density to just drop right off. Artifacting is a thing that comes up often in GIS analysis, and it's an important thing to look out for. A lot of times when I work with DEMs, there are artifacts in the DEMs that when you create curvature rasters, you create slope rasters, you see these lines or these weird things in your data that aren't really there. They're not a function of the real data. They're a function of sort of how that data was gathered or how it's stored or how the calculations worked. And all of that is called artifacting. Here then is the point data as a reminder. It looks something like this. So we've got point data overlaid on that, and it doesn't match up at all with this hockey puck idea. So a better way of running those calculations is actually with the kernel density tool. In practice, I really don't use the point density tool that often. A much more effective way of aggregating this data is by running kernel density. And so the result of this is essentially that we can define a continuous way in which the weights start to fall off. So instead of this all or nothing, you're in or out, the weight of that observation drops off with distance. And there are many ways of sort of specifying how that drops off. So you can either have sort of a linear kind of a drop off, in which case we're imagining that the weight structure looks like a cone. But you could also drop off in a manner that you see sort of at the bottom here, that in 2 dimensions, obviously. But if you kind of mentally imagine rotating that about a vertical line from 0, what that would look like. And we'd essentially, again, weight nearby observations almost fully, but then sort of steeply drop off before asymptoting out to 0. This idea comes up in geography all the time. It's related to the gravity model, distance decay, spatial autocorrelation. All of these are sort of similar ideas representing a core concept that nearer things are related, more related than distant things. In other words, the first law of geography. Kernel density has a lot of the same options as point density, so you can output a specific cell size. Again, I would encourage you to do that based on the data that you're working with. Don't just accept that weirdly calculated value. Try to round that off just like you would round off your legend values or your classification breaks. So we want to apply search radius. In other words, there's a maximum limit to which we want to include observations. And then you're going to specify, you're going to use a kind of a kernel. So in the case of ARC, you're a little bit limited in the kernels that you can use. You can't specify that. So it's going to be using this quadric kernel, which is what we saw before. Nearby observations are almost the same, but then it drops off very quickly. I wouldn't be too surprised to see those values or those options increase a little bit. It would be nice to at least have linear in there as an option or even exponential. And again, I would expect that probably to show up at some point. The last value that's really critical is the method of calculation. This is how the distance is calculated. You have two options, just like you do in a bunch of tools now in ArcGIS. You can specify planar or you can specify geodesic. Essentially, what this wants to do is it wants you to specify whether you think that the distance measurements already in your data and how it's projected are a good way to calculate distance, or if you want it to sort of translate those into effectively great circle distance. Why would you want to do one over the other? If your data is already in a coordinate system that makes sense for distance calculations like UTM or state plane coordinate system, you want to use planar because you've already sort of solved this problem by projecting your data. If you have left your data in WGS84 or lat long, you do not want to be using a planar method of calculation because your X and your Y directions are not equal. The lines of latitude stay the same, lines of longitude converge, and so you want to make sure that you're either projecting your data before you run your analysis or you want to use the geodesic method of calculation. That geodesic method of calculation is new. In Arc Desktop, that did not used to be an option. So it's really nice that a lot of these tools have included that, but be aware that it does add computation time to running the tool. Sometimes a lot, sometimes a little. And again, the better solution is to project your data. This is the same tool, this is the kernel density tool run on the same data. We use the same 500 meter search radius, but keep in mind that this 500 meters sort of the way that kernel drops off under kernel density is it drops off pretty quickly. So stuff at 500 meters is weighted next to nothing. Whereas in point density, it was weighted its full value. So under that tool, we saw these hard lines, and a lot of our hard lines go away here, and we start to see more rounded cluster. It's a little bit it's a little bit nicer to look at. I think you really can't say that all of the artifacts are gone, right? Because we don't necessarily think that these still circular features are probably really there. That we've probably over analyzed our surface a little bit here, but it's still much better than the previous tool. So even though we've talked about point density and we presented that, and I think it makes sense as a sort of a simple example conceptually, in practice it almost always makes sense to use kernel density rather than point density. It's just a much better tool and a much more reasonable way of expressing how we want to count data within a certain bandwidth. As we increase the size of our kernel, essentially we're reaching out a little bit further to weight observations. This is an example of what that looks like with a 1,250 meter search radius. Again, once you hit 1250, those observations aren't weighted very heavily, but they still count a little bit. And the result of this is that the whole thing kind of smudges out a little bit. We start to see coarser patterns, which may be a good thing. And there's really no right answer to what the right search radius is. And in fact, that's one of the complaints to this method, and why some GIS professionals will recommend using something like the hotspot tools, which we'll cover in the future, to do the same kind of work. But in effect, the point density tools, whether it's point density or kernel density, they allow you to manipulate things in a way that may be helpful, even if you're not necessarily getting a p-value of significance at the back end like you do with those tools. As we crank this up still further, you can start to see that almost all of the pattern is washed out. What we're really looking at here is sort of a model of essentially where the city is and where the core is. This kernel is obviously far too coarse to be effective here. But it's good to sort of see how those patterns come out. This is the point density toolkit used on the crime statistics for Chicago. The overall appearance of this is a lot better. We could still apply some of our other toolkits like focal statistics to this to smooth it out a little bit further. But mostly this looks a little bit better. Still some artifacting. Part of that artifacting is actually coming from the visualization scheme. So the sort of hard lines that you're seeing here are partly a function of how the symbology has been applied. But still a lot of artifacting going on here. And it's especially visible, once you get outside, you can really see how the points on the periphery show up as these circles. Again, think hockey puck. This is the KDE estimate on the same data. It's coarser. You still get artifacting on these sort of outlying points, but it's sort of hidden a little bit. But overall, this is a much better representation of what we're looking at. So these are all of these different methods kind of compared back to back, point to raster, point density, and kernel density. All three of these have some application in analysis. If I were sort of reaching for a toolbox, I'd probably reach for kernel density first. But point to raster has a lot of value as well. All of those values are true in the sense that each individual grid, each individual count, and each count in each grid is sort of directly measurable. Whereas tools like point density and kernel density are sort of reaching out and counting things that are sort of outside their grid cells boundaries. Again, that smooths things out a little bit, which is good. But sometimes if you just want to report on the exact value, point to raster is still valuable. So you'll get more experience with this stuff in the notebook. This is more of a theoretical introduction. You'll get the technical introduction there. And look forward to your questions. Thanks for listening, and we'll see you next time.